Welcome back to Unit H. Today's topic is, do other chemical reactions supply energy? So we've spent our first topic talking a lot about fuels, and different types of fuels and how they give us energy, and how we can tell if a fuel is better than another fuel. Remember those 11 questions that we asked ourselves. So now we're going to talk about how other types of chemical reactions can supply energy. Because in fact, fuels are not the only way to get energy out of a chemical reaction, and also this is an important topic because, as we know, fossil fuels are being readily depleted across the world, and so in the future we're going to need to move away from fossil fuels and look towards other types of energy to replace them. So it's important to understand how we might get energy from other types of chemical reactions as well. So, just as an introduction, there are many forms of energy that can be obtained from chemical reactions. So, last week we already talked about fuels burning to give us energy, and a fuel burning is a chemical reaction. And remember, we wrote the word equation out, where we had fuel plus oxygen giving us carbon dioxide, water, and energy, and we know that we're getting energy out, right, because we see heat and light produced. But like I said, fuels aren't the only type of chemical that can give us energy. The battery that you put in your phone or in your radio or in your anything that uses a battery, actually, that's all chemical reactions taking place to produce electricity. So and we'll talk a little bit more in detail in a minute about how batteries can produce electricity. And then there's other types of reactions as well, involving different metals and other things besides fuels that produce energy. So let's look specifically at one type of chemical reaction that gives us useful energy, and that's displacement reactions. So in Unit F, earlier this year, you guys looked at various chemical reactions, but not necessarily in a specific sense of how much energy they produce. Well, one type of energy that you looked at in Unit F was the displacement reaction, which is where you have a metal and you add it to a salt solution containing a different metal, and then those two metals swap places to give you two new products and useful energy. So, to be more specific, let's look at this picture that we have here on the left. This first picture. So we start with magnesium powder up here and copper sulfate solution. So that's when I was mentioning the salt of another metal. That's copper sulfate solution is a salt. And then after the reaction occurs, the two metals have swapped places, as you'll see. Now we have pieces of copper metal, and we have a magnesium sulfate solution. So you can see that the two metals just displaced each other, or swapped positions. And so here's the word equation for that diagram on the left. Magnesium plus copper sulfate goes to make copper metal plus a magnesium sulfate solution. And of course, the important part is that we get energy out of this reaction. But how do we know, or how might we predict how much energy we get out of a displacement reaction? So what we can use is what we call the reactivity series, which you should also be familiar with from Unit F. So as we can see, magnesium is higher on the list than copper. Therefore, magnesium is more reactive than copper, right? If we look here, the most reactive metal is at the top, the least reactive metal is at the bottom. So magnesium is able to displace the copper from the copper sulfate solution because magnesium is more reactive than copper. And the distance in between the two metals tells us how much energy will be released when they react. So now let's compare this to another displacement reaction. Let's say we start with aluminium, add it to an iron sulfate solution, and as we As we could predict, aluminum, if we look at our reactivity series, aluminum is more reactive than iron, so the aluminum will in fact displace the iron from the iron sulfate. So we'll get out iron metal and aluminium sulfate, and then also some energy. But see here I wrote energy in lowercase letters because the distance in between aluminium and iron on our reactivity series is a lot smaller than the distance in between magnesium and copper on our reactivity series. So the energy produced by aluminium displacing iron from iron sulfate is a lot less energy than magnesium and copper. So again, the distance in between the two metals on the reactivity series, that is the farther apart that they are listed on this chart, tells us how much energy we will produce. And again, in order for a metal to displace another metal, it has to be more reactive. For instance, if we look down at the very bottom here, if I add copper to a lead sulfate solution, well, let's go look at my reactivity series. Copper, is it more or less reactive than lead? Yeah, exactly. It's less reactive than lead. As we can see, lead is listed higher. So if I try to add copper to a lead sulfate solution, nothing's going to happen because copper is not more reactive than lead. So remember on the first slide, I told you guys that batteries convert chemical energy into electricity. But how exactly does this happen? So there's actually a cool phenomenon that happens if we add two different metals into a solution that we call an electrolyte, which is just a fancy word for a liquid that conducts electricity. So, for instance, tap water could be an electrolyte, but usually we like to make them extra. To make an electrolyte an extra good conductor, we add more salts or other things like that help conduct electricity. So anyways, so if we have two different metals in an electrolyte solution, we actually produce an electric current. So that's what that picture down here on the left is showing us. That if we have two metals, for instance, copper and zinc, and we add them into an electrolyte solution, which is the blue solution in this beaker, then if we hook up two wires or two leads to the metals, they will actually produce electrons that will flow around in the circuit and produce a current. And again, we can predict how much voltage or how much energy we will get by looking at a reactivity series. So here up in the right hand corner again is a reactivity series, a little bit different than the one that we used on the last slide, but it's the same idea. The metals that are listed higher are more reactive. And so if we look for copper and zinc, which are our two metals in our beaker, yeah, they're fairly far apart. They're going to produce a decent voltage. We can see the voltage is about 1.5 if we look on our voltmeter. But what if, and I'm going to clear my drawings off here, what if I, instead of using zinc, let's say I used sodium. So sodium's abbreviation is Na. So what if instead of using zinc, I use sodium? Well, let's go and look back at our reactivity series. So copper we already know is down here. And zinc, which we used at first, is here. Sodium is way up here. So what's going to happen to my energy produced as I switch from zinc to sodium? Yeah, exactly. So if this was how much energy I was producing before, now that I've switched to sodium, I'm going to be making even more energy, and thus my voltage meter will move up, and I'll get more voltage out. So that's the idea behind batteries. In batteries, there's two different metals, usually in an acidic solution. That's what battery acid is. That's the electrolyte used, and the two different metals then can produce a current and produce the electricity that we get out of batteries. And if you ever look on the back of your cell phone battery, it's usually what they call a lithium-ion battery. So looking at our reactivity series over here, and again I'm going to clear my drawings. So if we look again at our reactivity series, why do you think cell phone batteries would use lithium as one of their two metals? Yeah, exactly. Lithium's way up here at the top of my reactivity series. So no matter what my other metal is, I'm going to be able to produce a lot of electricity and a lot of voltage using lithium as one of my two metals, because it's the most reactive, at least one of the most reactive and the most reactive on this list of any of the other metals. So that's, if you see a cell phone battery that says lithium ion, then you know why. It's because lithium is the most reactive. Alright, let's just wrap up talking about another type of energy that we can get from chemicals. So, and fuel cells were discovered originally in 1850 by William Grove, but it's taken a long time for them to become more popular and more widespread. But what fuel cells do is they can convert chemical energy directly to electric energy, which is similar to a battery, right? And on the last slide we talked about how batteries can convert chemical energy into electric current. But the advantage of a fuel cell over a battery is that it can be refilled like petrol. That's why it's called a fuel cell, right? So just a normal cell or a normal battery eventually goes flat, right? It eventually dies. But a fuel cell can be given extra fuel or extra chemicals to keep it running, so it can be refilled unlike a battery. And the most common fuel cell that's currently in production is the hydrogen fuel cell, in which the fuel obviously then would be hydrogen, which, if we look at our figure, hydrogen comes into the fuel cell, and electrons are stripped from the hydrogen. Those electrons are able to flow through this circuit, and the electrons meet up again, and electrons, hydrogen, and oxygen combine to make H2O. So the cool thing about fuel cells is that there's no burning involved, so we don't have any carbon dioxide pollution. The only product that we get out of a hydrogen fuel cell is water, which isn't much of a pollutant. So that's the idea behind fuel cells. So let's just quickly wrap up what we talked about today. So, other than fuels, we've learned that there's other types of chemical reactions that supply energy. For instance, batteries that we use in various electronic devices, or metals such as magnesium and other chemicals that can produce useful types of energy, such as heat and light. And let me clear the ink here. So, one specific type of reaction that gives us energy is displacement reactions, where if we add one metal to a salt solution of another metal, we get a displacement and energy is released. But remember that the metal that we add has to be more reactive than the metal in solution. If it's not, then we get no reaction. That's key. And finally, we talked about how batteries produce electric current, and that is, if you have two different metals in an electrolyte solution, you will produce electrons that will flow around in a circuit and produce a current, produce a voltage. And remember, the same principle applies, that the distance in between two metals on the reactivity series tells us how much current, how much voltage that we will produce. And one promising new type of energy that might be able to replace fossil fuels one day is the fuel cell, where nothing needs to be burned, and so no pollution is produced, but we still get a lot of useful energy in the form of electricity. Alright, thanks for joining us, and we'll see you back next time for Unit H3, what new materials can we make from chemicals. Thanks.